Hi, welcome to Chapter 11, Overview Part 3, where we're going to talk about vapor pressure and phase diagrams. So let's talk about vapor pressure, okay? Remember these graphs from last chapter? As you notice, as we go to a higher temperature, the peak of your distribution gets lower, but it gets wider, so you have more particles that are at a higher speed, okay? If these particles are moving at a higher speed and they are near the surface, they can actually jump into the gas phase. And that is related to your vapor pressure. So at any temperature, some of your liquid molecules will escape from the surface into the gas phase. As the temperature rises, as we showed here, you will get more particles that jump into the gas phase. So as the temperature rises, the fraction of molecules that have enough energy to break free will increase. Okay, so here you have some liquid, and this is an empty container. You put some liquid in this container and you let it sit. And you see that some of the liquid will actually vaporize and become vapor above the liquid. These vapor particles actually have pressure associated with them, and that's called vapor pressure. Okay, and then here, as you wait until it comes to equilibrium, you will see that you have what's called equilibrium vapor pressure. Some of the particles are jumping into the gas phase, which is shown here, and some of the gas particles are going back into the liquid. Okay, so this is your equilibrium vapor pressure. So as more molecules escape the liquid into the gas phase, the pressure will increase until you reach your equilibrium pressure. So the liquid and the vapor pressure will reach a state of dynamic equilibrium. That's when the liquid is vaporizing at the same rate that the gas is condensing. Okay, and that is called your equilibrium vapor pressure. So what does equilibrium vapor pressure mean? So say you have a sealed container that you put a liquid in, and you wait. After a little bit of time, you're going to see that some of the liquid vapors will evaporate into the gas phase because they have kinetic energy, they're near the surface, and they're just going to jump into the gas phase. Then you wait a little bit longer, and you're going to actually get some more that escape into the gas phase until you reach an equilibrium rate, where the ones that are jumping into the gas phase are equal to the ones that are going from the gas phase to the liquid. So what you have in here is what's called your equilibrium vapor pressure. We'll call that VP for short. So what is it? It's the pressure exerted by a vapor in equilibrium with its corresponding liquid at a certain temperature. So your equilibrium vapor pressure depends on temperature. Okay? So if you raise the temperature, your equilibrium vapor pressure will increase because now more of the particles are jumping into the gas phase. So the amount of pressure you have in this container really depends on the amount of gas particles. So your pressure depends on the amount of gas molecules. So that's why when you raise the temperature, you're going to get more of the liquid into the gas phase, so your equilibrium vapor pressure will increase. So how do attractive forces affect equilibrium vapor pressure? Okay, so each liquid has a specific equilibrium vapor pressure at a given temperature because it has certain forces of attraction between the particles. The stronger your attraction, so the stronger your intermolecular forces, the lower your equilibrium vapor pressure. And let's think about that for a minute. Equilibrium vapor pressure is dependent on how many gas particles are above your liquid. So if your intermolecular forces are very strong, you're going to vaporize less molecules. So you will have less gas molecules above the liquid, so your equilibrium vapor pressure will be lower. Volatile means that it wants to change very readily. It wants to vaporize very quickly. So that's what volatile means. It's unstable, wants to change. So your volatile liquids have high equilibrium vapor pressure, and they will evaporate very quickly. Okay, why do they have high equilibrium? Because they have weak intermolecular forces. So the particles could go into the vapor phase very easily. So you have a lot of gas molecules, so you have high equilibrium vapor pressure. Okay, and so here is the corresponding thing that you need to remember. If you have high equilibrium vapor pressure, you evaporate quickly. Because the liquid will turn into a gas very easily. So if you're not in a sealed container, it'll turn into a gas and just disappear and evaporate. Okay, so let's look at these two substances here. Which substance will have a lower equilibrium vapor pressure, water or methane? So think about it. Which one has a stronger intermolecular force? Well, that would be water because it has hydrogen bonding. So water will have a lower equilibrium vapor pressure. Which substance is more volatile? The one that has the weaker intermolecular forces, and that would be methane. Which substance will evaporate the quickest? The one with the weakest intermolecular forces and the highest vapor pressure, which is methane. So here is a plot of vapor pressures, okay? So here you have temperature versus vapor pressure. And what do you notice? As you raise the temperature, what's happening to your vapor pressure for all of these substances? So as temperature increases, vapor pressure increases. And the reason why is you're breaking more intermolecular forces, allowing more of the liquid to become a gas, so you have a higher pressure above the liquid. The boiling point of a liquid is when the vapor pressure equals the atmospheric pressure. So assume you have a beaker of water and you're trying to boil it. You have atmospheric pressure pushing down on it, holding it in the liquid form, and you are heating it. So this is getting hotter. The particles are moving faster, 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 faster. And finally, they're going to jump into the gas phase. In order to jump into the gas phase, there's two things they have to overcome. You have to break your intermolecular forces, and you have to have enough energy to kind of overcome this atmospheric pressure. So the vapor pressure has to equal your atmospheric pressure. And this is used for cooking, okay? So most of you know what a pressure cooker is. So in your pressure cooker, your atmospheric pressure is not atmospheres anymore. It's at a higher pressure. So that means you would have to heat the water to a higher temperature in order to get it to boil. So since the water is at a higher temperature, it cooks faster. That's how a pressure cooker works. Okay, then there's something called normal boiling. Normal boiling is the temperature at which a substance boils under normal pressure, which is 760 torr or 1 atmosphere or 101.3 kPa. Okay, so you'd go up here and here's your normal pressure. You read it across, see where it hits that line, and that tells you your normal boiling. Lo and behold, the normal boiling for water is 100 because it's at that pressure. If you change the pressure, then the boiling temperature will change. Look, if you lower the pressure, you're now boiling at a temperature lower than 100. If you do what a pressure cooker does, increase the pressure, you're now boiling at a temperature higher than 100. Here is a way to calculate your heat vaporization, okay? So if you plot the natural log of the pressure on your y versus 1 over t, the slope of this will give you your enthalpy of vaporization. over R. R is the gas constant. So let's try to answer these questions. At room temperature, you have solid iodine. It's a molecular solid. Which of the following provides the characteristics of iodine with a correct explanation? It has a high melting point because it has weak intermolecular forces. Well, that doesn't make sense. If it has a high melting point, then your intermolecular forces should be pretty strong, right? It is hard because it forms a three-dimensional covalent network. No, that's not true either. It is not a good conductor of electricity because its valence electrons are localized in bonding and non-bonding pairs. Let's pause on that one and come back. It is very soluble in water because it is polar. Well, it is not polar. So the answer is C. Now let's look at number 2. Based on the data in the table on the left, which of the following substances has the weakest intermolecular forces? Well, what is the data showing us? Equilibrium vapor pressure. And what did we say about vapor pressure? If you have high equilibrium vapor pressure, you have weak intermolecular forces. So which one has the highest? So that means C has your weakest intermolecular forces. In the diagram to the right, which of the labeled arrows identifies hydrogen bonding in water? So let's look at A. A is the line between oxygen and hydrogen. That is a covalent bond. Let's look at B. B is a dotted line between the two oxygens. Now the oxygens have a partial negative charge on it. So B is a repulsive force because they are going to repel each other. They're not going to bond. Same thing with hydrogen. Hydrogen is this is also a repulsive force. And let's look at D. D is an attraction between the negative oxygen in one molecule and the positive hydrogen in another one. So D is your hydrogen bonding. Okay, now let's talk about phase diagrams. A phase diagram is a graph that shows the state of matter under pressure and temperature. So if you know the pressure and temperature of your substance, you look at this diagram, you can tell what state it'll be in. Will it be a solid? Will it be a liquid? Will it be a gas? The solid state is always in the lower temperatures, the liquid's in between, and then the gas is at the higher temperatures. The lines are where you have equilibrium. So on this particular line here, say you're here, you have solid and liquid in equilibrium because you are melting or freezing. So this line here is your melting or freezing points. This line here, you have liquid and gas in equilibrium. So this is your vaporization or condensation points. This line here, you have solid and gas in equilibrium. So you're either sublimating or deposition. This point right here is called your triple point, and at your triple point, you have solid, liquid, and gas in equilibrium. They all exist at that state. So let's look at these graphs a little bit closer. So we're going to focus right now on this curve right here, AB. So the AB line is your liquid vapor interface. You have liquid and gas in equilibrium. So the next time you're boiling water on the stove, look at it and realize that you have liquid and gas in equilibrium. Okay, so this is when you are either vaporizing or condensing. So this line here is your boiling points or your condensation points as a function of temperature and pressure. So it starts at A, which is your triple point, and it ends at B. B is your critical point. Above the critical point, no matter how much pressure you apply, you can never liquefy your gas. Okay? Each point on this line is the boiling point of the substance. So, can your boiling point change? Yes. It depends on the pressure. Okay? So, we normally talk about water boiling at 100. That's at normal pressure. You go across and you read it down and you get 100 for water boiling. Let's look at the next line, AD. In AD, you have solid and liquid in equilibrium. So this is melting or freezing along that line. And if you look at the slope here, the slope is positive. If you have a positive slope, that means that your solid has a higher density than your liquid state. Most substances have a positive slope. Because think about it, most substances, the solid is more dense than the liquid. The last curve, AC here, is where you have gas and solid. Okay, and below A, you cannot exist as a liquid. Cannot. But along this AC line, you have solid and gas. This is where you sublimate or deposit. So let's look at the phase diagram for water. Water is unique, okay? First of all, note the critical point. The critical point is very high. Very high. And that is due to its strong van der Waals forces, in particular its hydrogen bonding. What are some unusual features about the water? The slope of this line is not positive. It is actually negative. And since it is negative, it means the density of the solid is less than the density of liquid, which we kind of knew already because ice floats on water, right? Here's a zoomed up picture of it so you can see it is sloping backwards. And this is very interesting because say you are here and you increase the pressure. What happens to your ice? It turns into a liquid. So you can actually melt ice by just applying pressure to it. And this is why you can ice skate on ice. You can't ice skate on normal floors because when you step on them, they don't melt. But ice, when you step on it, the blade of the ice skate is so small that you're applying a high pressure, because remember, pressure is force over area, that you actually cause the ice to melt where the blade of the skate is contacting the ice, forming a layer of water on the ice, lubricating it so you could slide and ice skate past it. That's why you can't ice skate on most surfaces, because most solids, when you step on them and apply pressure, they are not going to melt. Okay, they are going to just stay a solid. Here's the phase diagram for carbon dioxide. What is so strange about this diagram? Well, look at the triple point. It's at 5 atmospheres. Okay, so and liquid is above that. So you can't have a liquid. You can't have liquid carbon dioxide below 5 atmospheres. Remember, our pressure is 1 atmosphere. So at 1 atmosphere, you're down here. Depending on the temperature, you're either a solid or a gas. There's no liquid. Below 5.11 atmospheres. So this is why carbon dioxide sublimes at normal pressure. So you keep it cold, it's a solid. As soon as you take it out and it warms up, it'll turn into a gas. That's why they use it when they ship food through the mail. It's a So it keeps the food cold, but it doesn't melt and form puddles everywhere. It just turns into a gas and evaporates away. Also, because it has a very low critical point, look at its critical point, 31 degrees. Because of that, it is used in many food processings, and you could make it supercritical, so it's a good solvent for extracting nonpolar substances such as caffeine. That's how they make decaffeinated substances. And that is the end of part 3.